Set 4 assumptions taken and derive the kinetic theory expression for the pressure, pure and ideal gas of density low and mean square speed c squared bar, which is given by pressure equal to a third density times the root mean times the mean square speed. Alright, so we shall consider this vessel where we shall place our gas. However, before we derive, we are required to give the assumptions. So let us first mention the assumptions here. We are going to consider ideal gas. So intermolecular forces of attraction are negligible. So that is one major characteristic of ideal gases. We assume that the force of attraction between molecules is negligible. 2, the duration of collision. So the second assumption is that the duration of collision is negligible compared to the time between collisions. So now we shall assume that this is A, B, C, D, and this surface here is E, F, G, H. So a molecule will collide from surface A, B, C, D. It will travel, collide with this surface, then come back. So as it collides with this surface here, E, F, G, H, the time taken there as it collides with the wall is negligible. By the way, it is a perfectly elastic collision. So when it comes from this opposite face and it collides with another face and it goes back, now the time taken here as it collides with the wall of the container is negligible compared to the time between collision. That means the time between two walls colliding with this wall of the vessel and then collide with the other wall of the vessel, the opposite wall. So in this case, the opposite walls we shall have A, B, C, D opposite to E, F, G, and H. So that is the meaning of this assumption. The third assumption here is that we are going to consider a large number of molecules moving in a random direction. So in this vessel, we are going to have a large number of molecules of gases moving in all directions. So we shall have random direction. There is no preference to where these molecules will go. They can go in any direction. They can go in the X direction, Y direction, Z direction. Alright. So, and another assumption would be so the volume of the gas is negligible compared to the volume of the vessel. Now the volume of the gas we have here will be smaller or negligible if we compare it with the volume of the vessel. So those are the major assumptions, but this one is very important, that we have a large number of molecules moving in random direction. Very, very important, because we shall make a deduction somewhere based on this assumption here. So now let us derive this expression for pressure. Now when we have a large number of molecules inside our vessel moving in a random or having a random motion, it means that the motion of this particle will have the component of velocity in x-axis, y-axis, and z-axis. In other words, these molecules have got freedom to move in any direction they want. So if we are to find the resultant velocity, we shall have c as our resultant velocity. So c squared will be equal to v squared plus u squared plus w squared. And if we are to take the mean speed, these are the square, mean square speed now would be the mean square speed in the y plus the mean square speed in the x plus the mean square speed in the z-axis. So the statement here is very important here. That is how we find the resultant. You should note that these gases are moving from organic field of matter. These gases are moving randomly, so their motion is in a 3 dimension. That's why we need to find the resultant speed of the molecules moving inside the vessel. Okay, so let us see what happens now when the gas is inside this vessel. So now we are going to first consider just one molecule. Remember, in the vessel we have a large number of molecules, so we shall first consider one molecule of a gas moving across or moving along the x-axis. Remember, along the x-axis the component of the speed is u, so across the opposite face of the tube. Now we shall consider a molecule moving across the opposite faces of the tube, meaning it will move from this face here, A, B, C, D, then it goes to the opposite and come back. So it will go and come back. So across the opposite face of the tube of dimension L, to and fro with speed u1. So since we are considering one molecule, we shall give it a speed u1, and the dimension of this tube is L, meaning from this face A, B, C, D to this opposite face E, F, G, H, the distance traveled or the distance between them is L, but the molecule is going to move to and fro. So from this face to the opposite face, then back, meaning the distance which will be traveled will be equal to 2L. The distance traveled here is going to be 2L. Now if it has a speed of u1, that means that it will have u1 going, then negative u1 back, because now this is an opposite speed. And now when it changes direction, we shall call it a negative speed because it is moving in opposite direction. So the velocity now, here we are going to be talking in terms of velocity because we have a change in direction. So u1 going, then negative u1 coming. So there is a change in speed, and therefore we expect a change in momentum. So what will happen if speed is changing, and what is the force when this molecule collide with this wall of the vessel and it come back? Don't forget the collision is perfectly elastic. It doesn't take much time here on the wall, so it will collide and then bounce off. So there is a large change in momentum and expect pressure. That pressure is what we are going to find. Now since we have seen that the molecule will have a speed u and then negative u1, there is a change in momentum. Let us look for that change in momentum. So the change in the momentum is going to be the initial momentum, which is mu, minus the final momentum, which is negative mu, where m is the mass of the molecule. Why are we taking negative mu? Because now we have this velocity when it bounces off. It will be opposite to this velocity which is coming. Same in magnitude but different direction. So that change in momentum is going to be mu plus mu, because this is minus. So we get 2 mu. By the way, it is mu1. That is the speed for one molecule along the x-axis. Of course, if we are using along the y-axis, we could be talking about the surface at the bottom and the surface at the top. and we should be giving that molecule maybe V1, but now we are considering Ux, so I'm giving it a U1. That is the reason I'm giving it a U1, because the X component has a velocity U. So for one molecule, let me call it U1. Alright, what about the time taken? Now the time taken between collision, I'm not talking about the time for collision, the duration for the collision, but the time between the collision. That means from phase ABCD to phase EFGH. So the time between collision. Now that time is going to be equal to distance traveled over the speed. So the distance traveled is going to be 2L, because to take L and L2, L back, so 2L, and now the speed is U1. So these are very important. We have seen the change in the momentum and the time taken. So the rate of change of momentum is directly proportional to the force. So we can find the force since we have got the change in momentum, and that was the objective of getting the time and the change in momentum, because we know from Newton's second law of motion, the rate of change in momentum is directly proportional to the applied force. So let us write the expression for the applied force using the rate of change in momentum and the time taken. So the rate of the change in momentum and the time taken. So since the change in the momentum is 2u1 and the time taken is 2L u1, by the way, don't forget this is one molecule. So the change in the momentum, we know from Newton's second law of motion, from Newton's second law, we know that the force will be equal to rate of change of momentum. So change in the momentum over the time taken. So the force, let me give it F1, that is the force for that one molecule, will be the change in momentum, which is 2u1 over change in momentum 2u1, then over time, which is 2L over u1. This is the same as 2u1 times u1 over 2L. And now this will be, okay, this was 2mu1, change in momentum. Sorry about that. 2mu1. So same here, 2mu1. mu1. So now if we simplify, we can see that this 2 goes that 2, then we have the force as mu1 squared over the L. L is the dimension of the cube. So that is the force. By the way, I keep reminding you that this is the force for just one molecule, but remember we have a large number of molecules. So let us now get the total force exerted by that large number of molecules. So to get the total force, we are going to get the force of all the molecules. So that will be m over L. It was u1 for the one molecule, u1 squared, plus now u2 squared, plus up to un squared. So this is going to be the total force for all molecules inside the vessel, which will collide with this surface here from ABCD to EFGH. Now let u squared be the mean square speed, and by the way, this is the mean square speed along the x-axis. We are still considering only the x-axis, so that means that u bar squared, the mean, we shall add this and divide by n. It will be u1 squared plus u2 squared plus up to un squared divided by n, where n is the total number of molecules inside the vessel. So after here, of course, you can see that this one can be written as u1 squared plus u2 squared plus u3 squared plus up to un squared can be taken to be n times the mean square speed along the x-axis. So from here we can see that the total force is the same as m. Now we have seen that when the summation of all these can be written as n, then u squared bar, where this stands for the mean square speed, then divided by L. So that is the total force exerted by all the molecules inside the vessel on the surface E, F, G, H. Okay, now since we have the force, we can now find the pressure. So if this is the total force, then we know that pressure is equal to force over area, but our area, now we shall consider the cross-section area of this vessel, which is going to be L squared. And now the force is here. That means that the pressure is going to be this force over the area, which is mn u squared bar divided by L cubed. So this is the pressure. However, we need to bring in the resultant mean speed. How do we do that? Now, for large molecules, remember we made that assumption that for large number of molecules, we shall note that if we have a large number of molecules here, and for large number of molecules, the speed along the x-axis is equal to the speed along the y-axis and is equal to the speed along the z-axis, implying that v squared bar is equal to u squared bar is equal to w squared bar. These are the mean square speeds in y, x, and z axis. Now from here, it would mean that the resultant mean square speed will be equal to 3 u, because we've been using u squared bar, so it will be equal to 3 u squared bar. So there is a need to use the resultant. That's why we considered even the large number of molecules, so that we are going to generalize now. So it implies that our u squared bar, the mean square speed along the x-axis, can be replaced with a third of the resultant mean square speed. So we come back here and we substitute. So we shall say that our pressure is going to be equal to m n over L cubed, then times a third c squared bar. And now when you look at this is the total mass. M was the mass of one molecule and N the number of molecules, so this is the total mass over volume. So N over L cubed is equal to density, which is rho. So pressure is given by a third rho, which is the density, times the, by the way, this is the resultant now, times the mean square speed. And this is the expression for the kinetic pressure of a gas, an ideal gas in particular.